The most widely used hydraulic shock absorber is the direct-acting telescopic type. It can be fitted as a self-contained unit or combined with a suspension strut. The strut type uses the same principle of operation, but it is considerably larger. The hydraulic shock absorber provides its dampening action by transferring oil under pressure through valves which restrict the oil flow. The twin tube type is the most common. The outer tube is normally attached to the suspension member at its base, and the inner tube provides a working cylinder for a piston which is attached to a piston rod. The piston rod is connected to the frame at its outer end, and a bearing at the top of the outer tube keeps the rod in alignment as it moves in and out of the shock absorber with suspension action. A seal above the bearing prevents oil leakage and keeps out dirt and moisture. A shroud protects the rod from damage. During bumps or compression, the rod and its piston move into the shock absorber. In rebound or extension, the rod and piston move out of the shock absorber. For dampening to be effective, resistance is needed in both directions. This is provided by the oil and by disc valves attached to the piston and the base of the inner tube. Oil fills the inner tube and surrounds its outer surface to a level which allows a free space or reservoir to exist above it, between the inner and outer tubes. On bump or compression, the piston and rod move downwards in the cylinder, resulting in a small pressure drop in the chamber labeled A above the piston. At the same time, the volume of the chamber labeled B below the piston is reduced, causing a high fluid pressure. This unseats the piston intake valve, and fluid flows up through the outer passages in the piston and into chamber A. But the piston rod is also now entering A and displacing a quantity of fluid equal to its volume, so all of the oil in B cannot flow into A. The displaced fluid is forced down through a base valve and out into the reservoir labeled C. In the rebound or extension phase, the piston and rod move upwards and the volume of chamber A is reduced. Chamber A becomes a high-pressure area, and fluid flows through the extension valve in the piston into chamber B. However, the withdrawal of the piston from B greatly increases its volume, and fluid flow from A is insufficient to fill the space. Pressure in B falls below that of the reservoir, causing the base intake valve to be unseated. Fluid flows from the reservoir into chamber B, keeping the inner tube full. The valve provides control over the amount of force required to pass fluid through them at any given piston velocity. They can be made to open in stages, according to fluid pressure. This allows light resistance to motion when the piston moves slowly, and heavy resistance when piston velocity is high. The rapid movement of the piston, continually forcing the oil backwards and forwards through the valves, causes it to heat up, as it absorbs the energy of motion of the spring and converts it into heat. The heat is transferred through the outer tube to the outside air. However, the hotter the oil becomes, the greater its tendency to aerate. Aeration occurs because of the high velocity of the oil as it passes through the small passages in the valves. If the velocity is high enough, air dissolved in the oil comes out of the solution as small bubbles and forms a foam. Aerated oil has a certain amount of compressibility, so it is unable to provide the dampening force previously achieved in the non-aerated condition. The performance of the shock absorber is thus considerably reduced. This effect is called shock absorber fade.